the Signal Protocol as presented by Group 3, Karen Q and Samuel Jones. The Signal Protocol involves a number of different technologies. We will specifically be focusing on the double ratchet algorithm, prekeys, elliptic curves, and the triple Diffie-Hellman handshake. The Signal Protocol is divided into three main stages. The initial key exchange involves registration and session setup. During the registration phase, two users, Alice and Bob, would upload their identity with a key distribution server, and then upload their long-term, medium-term, and ephemeral public keys. Basically, during the session setup phase, Alice would request for and receive a set of Bob's public keys from the key distribution server, and then use those to compute a secret key which would later be used during the double ratcheting process. Then we have the asymmetric ratchet phase, which is where Alice and Bob alternate in sending new ephemeral Diffie-Hellman keys in this ping-pong kind of fashion. Then during the symmetric ratchet stage, we use key derivation functions to ratchet forward chaining keys to create symmetric encryption keys. Essentially, I, Karen, will be covering the initial key exchange, and then Samuel will cover the double ratchet algorithm. Typically, the Sesame protocol is used to handle the initial key exchange phase. It was designed to manage double ratchet sessions, but it can be used for other message encryption protocols. During the key registration phase, both Alice and Bob upload their pre-keys to the key distribution server. Pre-keys are keys that are published prior to starting the protocol. As shown on this slide, there are three different types of pre-keys: signed pre-keys, identity pre-keys, and one-time pre-keys. One-time pre-keys only last once per X3DH session, so Bob has to upload a set of these when he's uploading his pre-keys. If the server is running out of one-time pre-keys, then Bob will optionally have to upload more. Signed pre-keys are signed by Bob's private key. If Bob wants to upload a new signed pre-key, then he'll need to destroy the private key corresponding to his old signed pre-key. Bob decides how long the signed pre-keys will last. That could be weeks or months. The identity key lasts the longest and is bound to Bob's identity. In order to set up a session, Alice needs to first request and receive Bob's public keys in the form of a pre-key bundle. The pre-key bundle consists of Bob's public identity key, his current signed pre-key, his pre-key signature, and optionally a one-time pre-key. The underlying key exchange mechanism is known as the extended triple Diffie-Hellman protocol. It's also known as the triple Diffie-Hellman handshake. After receiving Bob's keys, there are two potential outcomes. One, Alice aborts if Bob's signature is invalid, and if it is valid, then Alice will proceed to compute the ephemeral key. Then Alice can proceed to make a secret key using elliptic curve Diffie-Hellman and HKDF, which is HMAC-based extract and expand key derivation. This secret key can then be used in the double ratcheting mechanism. X3DH provides forward secrecy and cryptographic deniability and asynchronicity to the Signal protocol. An elliptic curve is a set of solutions of the form y squared equals x to the power of 3 plus ax plus b. Elliptic curves have a special property in that a line drawn through them will have a point crossed over at some other point in the curve. Imagine that you have a billiard ball that you are throwing towards an elliptic curve, and every time it touches one of the points along the curve, it actually changes direction. That is kind of what elliptic curve cryptography is about. Given an elliptic curve and two other points, you will be able to derive a third unique point. Thus, we have the concept of point addition, where there is some integer n and a bunch of points that have been added together. When you only know what the first and the last points are, deriving n becomes very difficult, and thus it can be used instead of normal Diffie-Hellman. This is called ECDH. This is when, instead of using a multiplicative group of integers modulo prime p, we instead use a multiplicative group of points on an elliptic curve. AES is another technology involved in the Signal protocol. In 256-bit AES, there is 14 rounds of permutation and substitution. There are 4 main steps in AES, which is subbytes, shift rows, mix columns, and add round key. Now that Alice has her ephemeral key, she sends a message to Bob containing her identity key, her calculated ephemeral key, a statement containing what pre-keys of Bob she has used, and an encrypted ciphertext. Once Bob has received the message from Alice, he will be able to compute the secret key using the same series of calculations. Bob's side of the protocol is done if the ciphertext decrypts.
One of the most central and novel parts of the Signal protocol is the double ratchet key management algorithm. The design is a combination of two different key ratchets found in earlier end-to-end encrypted messaging protocols. The Diffie-Hellman ratchet, which is used in the off-the-record messaging protocol, and a symmetric key ratchet based on the one found in the silent circle instant messaging protocol. What is a ratchet anyway? A ratchet is a mechanism, like the one shown, that allows movement in one direction only. We can keep turning as many times as we like in one direction, but we can never go backwards. The mechanical analogy ratchet is used to describe the one-way property of continuously deriving keys through a HMAC key derivation function, or HKDF. A HKDF is a cryptographic hash function based on keyed hash message authentication code, or HMAC, that takes a value and a symmetric key and returns a fixed-length pseudo-random key that can be expanded into additional pseudo-random keys. In the Signal app, the primitive used is a deterministic hash function built on HMAC SHA-256 or 512. The output is a secure, pre-image resistant cryptographic hash of the key and value that is indistinguishable from random if the key is not known. KDF chains form the inner ratchet in the double ratchet algorithm. By using the output key of one KDF as the input key for a subsequent KDF, we can chain KDFs together. The KDF function takes two inputs, a key and some input value, and produces two outputs at each step. A different KDF key for the next ratchet step, and a separate message key that can be used as a symmetric key to encrypt or decrypt the message corresponding to that ratchet step. This gives us the following cryptographic properties. Forward secrecy. Even if a KDF key is compromised, the one-way nature of hashing means that past communication is still protected. Resilience. KDF function output appears random without knowledge of the KDF key. Knowledge or control of the input does not change this. And break-in recovery. By adding entropy to the input, future output keys will also appear random to an attacker, even if a KDF key has been compromised. Double ratchet combines three separate chains for each conversation. A root ratchet that gets its key material from a Diffie-Hellman exchange between the sender and receiver is then used to provide keys to the sending and receiving ratchets. The ratchets start with the same shared secret derived from the Diffie-Hellman exchange and then stay in sync as they are advanced with each message sent and received. For the symmetric key ratchets, every message that is sent or received has its own unique message key generated from the previous output chain key and a constant input. Each chain key incrementation is a ratchet step. After each step, the chain keys get deleted, but the message keys can be kept, which is useful for decrypting messages that get lost or arrived out of order. This is better suited to mobile, asynchronous communication, since the ratchet can continue to advance even if a message is missed. Signal uses extended triple Diffie-Hellman elliptic curve cryptography with either X25519 or X448 curves. The Diffie-Hellman ratchet advances with each message sent, calculating a new public-private key pair. Every message header contains the public key for their DH ratchet's current step. Symmetric keys for the root and sending chains shown on previous steps are derived by combining the sender's public key and the receiver's private key. When we use symmetric key ratchets inside a Diffie-Hellman ratchet, we get the double ratchet. The output from the DH ratchet is used to create a root key from which the sending and receiving KDF chains are derived. The protocol allows a max number of ratchet steps that can occur in the inner KDF chains without advancing the outer Diffie-Hellman ratchet, which is useful in case of missed or dropped messages. But in normal operation, the DH ratchet is advanced with every message. After each DH exchange, the old root keys get deleted, leaving just the message keys. These are kept in case messages arrive out of order. The pseudo-random and pre-image resistant nature of HKDF functions means the message keys cannot be used to derive other keys. The double ratchet provides a self-healing cryptographic chain where the inner ratchet provides forward secrecy and the DH ratchet provides backwards or post-compromise secrecy. This is extremely important in an asynchronous messaging protocol where a chat session may span years, since breaking one key would expose all the messages sent after that key. The Diffie-Hellman exchange enables parties to share a secret over an insecure channel. By using pre-key bundles, asynchronous messaging is well supported, since messages can be encrypted without needing to first establish contact with a remote client, and messages can be refreshed, within limits, without the sender needing to have contact with either the server or the remote client. By changing encryption keys with every message, replay attacks are also not possible.